So I guess we have some questions to do here. Mm, Deflection of radio photons in the gravitational field of solar system bodies. We have some guys here, some great scientists, and who measured the deflection of light coming from stars, apparently very close to the sun during the total solar eclipse in 1919. The deflection was found to agree with the theoretically predicted value of 1.75 arcseconds. Um, we have this we have this light to a photon which passes through sun. We are given this relation, so I think I'm supposed to do. Yep, we're supposed to do this. Is it possible to detect a deflection of radio photons from a quasar? So yeah, um some time ago I did this, so I'll try to explain at the best way possible. I've given this I've drawn this simple analogy where this is the sun, this is the earth, and it's a light coming from a star, which is this is the true position of the star. So and delta theta has to be this deflection, and from earth we apparently see the star right here. In the equation it is given for, okay, let me write, it's given from stars which are apparently very close to the sun. So uh, this would imply that distance will be equal to the radius of sun. I've done the same thing right here. So we're already given this relation which is delta theta is directly proportional to this relation. So we have this c square, and instead of d we will write r naught. So what we're asked to find is whether it is possible to detect a deflection of radio photons from a quasar. So we're given to mark yes or no for reflection seen from Jupiter and the moon, right? Where whether we are able to detect it. So to be able to detect it, our value, our value must be at least equal to or greater than this one, because our the present day accuracy is 0.1 MAS. Therefore, the deflection, by that I mean the delta theta, must be equal to or greater than 0.1 ms. So um it's actually quite easy. So right here, what I would like to do is this Poise constant, J is constant, and we have this c square is also constant. So we have this delta theta, which is directly proportional to mass divided by radius, right? So in order to find the deflection for this from this Jupiter, we are given delta theta 1 regular percent to m1 by r1 and delta theta 2 m2 by r2. So because these constants will cancel out, we can just do delta theta 1 by delta theta 2 equals, let's say, m1 by r1 divided by m2 by r2, right? So just put the values for Jupiter and Sun. So you can take delta theta 1 as, you know, this deflection from Jupiter, and delta theta 2 as deflection from Sun. And we are given the deflection of Sun as, yes, so 1.75. It's just 1 point, okay, I'm sorry, 1.75 arc seconds. Therefore, what I would like you to do is so we have this delta theta z by delta theta s, which will be equal to this mj by rj, as I've already told you, and um delta theta s, so ms by rs, right? Just put in the values. So delta theta j will be equal to this thing right here, right? This thing right here divided, I mean multiplied by delta theta s, which is in fact 1.75 arc seconds. So by putting in all the values, we get delta theta z as mm, let me see what I've okay. It comes as 0.0167 arc seconds, which is 16.7 milliarc seconds. Just put in these values, you will get it. So, are we able to detect it? Are we able to detect this radio photons from a quasar by Jupiter? Yes, of course, because it is very, very greater. I mean, significantly greater than 0.1 ms. So, yes, we can. Similarly, do the same thing for, I don't know, do the same thing for Moon. So, for Moon, it will be delta theta m equals the same thing right here, m moon by r moon, okay, m moon by r moon divided by m sun by r sun, okay. Yes, this we generally denote this as a sun, right? So if we are going to denote sun, we use this symbol, so it doesn't really matter anyways. um Multiplied by, we have this 1.75 arc seconds, or you could actually multiply it with this, what we have, 0.0167 arc seconds if you want, but for that you'll need to write this mass of Jupiter and the radius of Jupiter. So yep, and I get this delta theta m as 0.4026 arc seconds, which is let's just multiply it by this, which is 0.026 mas, which is smaller than 0.1 mas, 0.1 mas. Therefore, you are not able to detect it from moon, by moon. Yeah. So let's go to another question. The Virgo cluster of galaxies. This is an easy one. You just said this. So this is the distance indicator from which method we use to find the distance to the galaxies, right? So we have here from Cepheids, we have this distance. I mean, distance to the Virgo cluster as this, and from this method we have this, from this method we have this is one. So this question takes into account the weighted mean. So it's actually easy. We're given the formula right here. So what we were asked is, by applying a weighted mean, compute the average distance. So average distance will be summation weight multiplied by the distance divided by the weight. And we have this weight, which is given by 1 by uncertainty squared. Mm, yeah, like unlike usual mean, we have this weighted mean because it's more accurate. And typically we use weighted mean in more practical terms in real life. So yeah, that is it. Therefore you'll just use this formula, right? Which is, and we have this weight multiplied by distance as distance divided by the uncertainty square. So here what you see, SI or this sigma, same thing. Okay, SIS sigma, this is the same thing. I just wrote it right here. Um, we're given this weight as 1 divided by the square of uncertainty, which is just these values after the main values right there, right? For this, it is 1.5. For this, it is 2.4. For this, it is 5.0. Okay, so we have the distance, which is given by just this. I just got bored to make a table. You can just make the table. It is just filling in the values right here and calculating this, and you get this sum as 3.548 and this sum of the product, right? Product sum as 5.94. So you just calculate the distance by plugging in the formula. Another question what we are asked is what is the uncertainty RMS in that estimate? So uncertainty means this root mean square, right? Um, so uncertainty in the weighted mean, uncertainty in the distance, average distance we have calculated the true distance. It will be the root of the it will be the root of this, what we call it. I'm sorry, weighted mean. One by sum of the weighted mean. Okay, I mean weight. So, and this again we have already calculated, which is going to be 3.548. So just plug in the formula. These are all already given in the question, and we know the uncertainty RMS and that estimate. The formula is, you know, this one. Everybody knows this actually, so not a big thing. Yep. So we have this uncertainty in weighted mean as root 1 divided by 3.548, which we have already calculated, which is 0.53 megapascal. I'm not dealing with error at this time. We'll do it later on, but anyways, let's go to question number 3, which is spectra of the galaxies in Virgo indicate an average rotational velocity of 1136 kilometer per second for the cluster. Can you estimate the Hubble's constant? So Hubble's constant, V equals hd. Everybody knows this. So h is going to be written as this one right here. So we're given this v, where we have calculated this average distance, so we get this Hubble's constant, right? So uncertainty, to find the uncertainty in Hubble's constant, the calculation which we have just done, we use the error propagation, which is for anything which depends on a and b. If x depends on a and b, we have this right here, delta by a plus delta b by b, right? Delta x by x, delta x by x equals this one. So delta x is going to be delta by a plus delta b by b multiplied by x. The same thing we have done here. Just plug in the values, we get this easy one. A fourth question is what is the Hubble time? Hubble time is Hubble time is 1 by the Hubble's constant, which is just the reciprocal of Hubble's constant. It's quite an easy question actually. This whole question is really easy. I've done it like a million times. Um, just do this and convert this thing into all seconds. So to convert into SI unit, you just multiply it by meters, you just divide by 10 to the power 6. And for PC, we have 3.26 light years. So 3.26 times 9.45 times 10 to the power, I guess, 15 or something like that. Was the value of light year. Just multiply it, you will get this in seconds, and divided by 1 year, because we are going to calculate the time in terms of years. So if we divide by 1 year, 1 year has this 86,400 multiplied by 365 seconds. So we get this 13.56 billion years. So also to estimate an error in the estimation of Hubble time, we have this, sorry, we have this formula. So um it's actually easy. So S means just a standard deviation, or let's say uncertainty. Okay, uncertainty. So we have already calculated this 2.4 thing right here. We have calculated the uncertainty in error propagation. So we'll have this STS by TS equals SS naught by H naught, which is given by 2.4 divided by 2.1, which is 0.03 approximately. So yeah, so in the uncertainty in time, we will just multiply this by this, because as uncertainty in Hubble's time equals S naught by S naught multiplied by TH. Just the same concept we use here. It is exactly the same concept. Okay, it is exactly the same concept. And we get this. Oh, the question is finished. So yeah, this was it for this question number two. Let's go to another question. I just wanted to include some easier questions as well. So this is actually the easiest one of all ever given in IOA. I think it's IOA 2007 and IOA 2011. Um, a crater on the surface of the moon has a diameter of 80 kilometer. So what we need to know is from small angle approximation. We have this D, we have this D here, and you know, just a small angle approximation. This is not this rocket science anything. We get tan theta as a d by d, and for a small angles like tan theta is approximately equal to d, right? Um, what was it saying? Tuesday 9 January in my on my iPad. Okay, anyways, so theta equals d by d. And I've done the same thing right here. It is the diameter, whereas it is the distance to the moon, and we get this, you know, the angular, I don't know, the angle, this angle, which is angular diameter of this crater on the surface of the moon. So to resolve the crater with naked eyes, we have this Rayleigh criterion formula. I don't know how to pronounce it. Rayleigh criterion. Okay, this is 1.22, and this is the wavelength of visible light. Yeah, I guess right here. And 5 times 10 to the power minus 3 is our episode of the bell. So we get this as 1.22 times 10 to the power minus 4 radian. Remember, it is always in radians. So the minimum angle that can be separated by our pupil, by our eyes, is this. And yeah, we get the angular diameter as this, which is really greater than the minimum angle. Then we can resolve it, not a rocket science. Question number two: what will be the diameter of a radio telescope working at a wavelength of lambda equals 1 centimeter with the same resolution as an optical telescope of diameter? Same concept, nothing, what? Nothing big. Okay, so we just compare this for equal resolution, same concept, and 1.22 will be cut, cancel, and d2 will be equals to d1 times lambda 2 by d1. Here are the necessary given formulas. Just plug in and it will be 2 kilometer, not a rocket science. So I'll just go hop into another question. So this is the easiest one. Okay, for this one, we have a sun orbiting periodic comet is, bro. This is the easiest one. Five. So this is the aphelion and this is the perihelion, right? So you get this just like this. It's going to be really easy for you 16 AU, and by Kepler's third law, we do have p square equals a cube, and w- we can use this relation when, you know, I guess p is in years and a is in AU, or p is in years and both. A equals AU. We will have we'll have what? We'll have p squared equals a cube. We can use this instead of using this lengthy formula like this. Why to use this formula? Easy one. So our period will come as what? Mm, our period is 64 years. So another another one for a comet in question number one above. What is the area in oh, area swept. So for an ellipse, we know by Kepler's law, planets orbit in ellipses, right? So area of an ellipse is pi AB. We know area of a circle is pi r squared, and it's the same everywhere. But for an ellipse, it's different, right? It is B, it is A to A, right? So yep, pi AB. For circle, it is pi times A, same thing. So no problem, not a big thing. So area of an ellipse is given by pi AB. We're just doing things like we have we have A. So what do we need is B, and we know B square equals A square 1 minus C square. And what we need to calculate also is RP, which is distance of perihelion from the focus where there is the star, where the star is. We have RP equals A1 minus E, minus in the sense that it is closer. Like for perihelion, you will have 1 plus E. So RP equals A1 minus E, and you have the A right here, and you have the perihelion just right there. You will get E, and using this formula and plugging in all the values, you will get B. So just calculate this um, area. And what we have is area swept per year, and per year doesn't mean Earth year in this question. Per year means its own orbital period, which is 64 Earth years. Which is 64 Earth years, right? So, yep, it's 64. What the hell is this? We have calculated period is 64 Earth years. So, mhm, so it's just, yep, 3.12 A square per year. It just swipes this area per Earth year, I guess, per Earth year. This is it. I think this was it. I think, I suppose. Okay, question number three. Most single appearance comets entered the solar system directly from Oort cloud. Yep, Oort cloud. You know, you have the solar system, we have this Heliopause, and we have this Oort cloud, right? Um, Estimate how long it takes going to make the sun. Assume that in the Oort cloud, 35,000 AU from the sun, the comet was at aphelion. So we're given the distance of aphelion, and uh, we actually need to find the perihelion, I guess. Yep, perihelion, because perihelion would mean that when it enters the inner solar system, it would mean perihelion. I will make you understand this really easy. So we have this semi-major axis, which is given by Ra plus Rp divided by 2. So it's as easy as it is. So Ra plus Rp divided by 2, we have um 35,000 AU right here. So 35,000 divided by 2 will be 17,500 AU, right? Which is the semi-major axis. So p square equals a cube. Just plug in the formulas, we'll have this much years. So time taken to reach the inner solar system, and it is a crazy one. I mean, it is kind of a common sense if you see, like, it will be just half of the period, the whole period to enter the solar system. So we will just divide it by 2, and we will get this here, which is approximately 1 million years. Yeah, because as you see, it says how long it takes a comet to make this journey, and we have enter the inner solar system directly from the Oort cloud, and it's a single appearance comet. So we'll have period which is the double the time taken, right? And same concept is reused right here. I suppose this is it for today. It was really fun. Thank you.